cabut ya. Oh, pointer yang mau share-share ini nggak usah, nggak apa-apa. Harusnya aman. I still, yes, we're right. But you didn't share any. Yes. Yeah. Just yes, now it's working as well. Yes. Yep. Okay, that's all done. Everything is good. Yeah. I guess how it works. But in this case, you actually simply like pause and you zoom. So basically, that's what it's like. Because we want to have zoom. Also on that screen, right? Yeah. So I think it's okay. Okay. So that they can see. Oh, you want me to see that? Yes. Oh, you can see that. Yeah. Because the camera is good. Yeah. Now I think the camera actually. They also have to see that. But now in the power camera, the boy time. Okay. Yep. Powerful. Tapi kan di depannya ada screen. Ya, tadi. Ya, ada masalah. Ini mau power ya. Oh. Just a bit. I think something would happen. Apa? Jadi, oke. Apa? Jadi buka.
Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sejahtera bagi kita semua. Shalom, Om Swastiastu, Namo Buddhaya, dan salam kebajikan. Yang terhormat, Direktur Riset dan Pengembangan Universitas Indonesia, Bapak Munawar Halil, SSI, MN, SC, PhD. Yang terhormat, Sales Director Branker Biospin, Mr. Hwan Chai Fongwanton. Yang terhormat, Business Development Manager, Mr. Hong Teng Aun. Yang kami hormati, Application Specialist Branker Biospin, Dr. Tan Sing Ho. Yang terhormat, General Manager Branker AXS Division, PT Dynatech International, Bapak Ardian Syah. Yang kami hormati, Bapak Yanuar, selaku Sales Management Branker AXS Division PT Dynatech International. Dynatech International, mohon maaf. Dan seluruh hadirin peserta seminar, baik yang hadir secara luring maupun daring. Puji syukur kepada Tuhan Yang Maha Esa, karena hanya atas izinnya, pada hari ini kita dapat berkumpul di auditorium lantai 2 Gedung ILRC, Universitas Indonesia. Perkenalkan, saya Nur Indah Iriana, pembawa acara pada hari ini. Selamat datang di acara seminar Basic to Advanced NMR Nuclear Magnetic Resonance Application. Acara ini diselenggarakan oleh Direktorat Riset dan Pengembangan Universitas Indonesia. Bekerja sama dengan Branker Biospin dan Dynatech International, acara ini bertujuan untuk berbagi pengetahuan terkait aplikasi NMR, utamanya dalam dunia riset dan analisis, serta memperkenalkan instrumen dan layanan NMR di Universitas Indonesia. Hadirin yang kami hormati, sebelum kita memulai acara pada pagi hari ini, izinkan saya membacakan tata tertib seminar pada pagi hari ini. Oke, bisa kita lihat di layar tata tertib seminar pada pagi hari ini. Yang pertama, untuk peserta yang berada melalui Zoom, mohon mengganti namanya dengan profile format nama _ instansi dengan memasang virtual background yang sudah dikirimkan panitia melalui email. Peserta yang akan mengajukan pertanyaan dapat menyampaikan di sesi diskusi dan tanya jawab untuk peserta luring atau pertanyaan pada kolom chat untuk peserta daring. Peserta yang bergabung melalui Zoom dimohon untuk tidak mengirimkan chat selain dari pertanyaan kepada pembicara karena akan menyulitkan rekapitulasi pertanyaan. Yang keempat, peserta akan memperoleh e-sertifikat apabila mengikuti semua rangkaian kegiatan secara penuh, mengisi daftar hadir untuk peserta luring, dan menyertakan bukti screenshot kehadiran pada tautan absensi untuk peserta daring. Lalu yang kelima, tautan absensi dan feedback akan disampaikan panitia pada chat room Zoom untuk peserta daring. Selanjutnya, ada informasi tambahan. Untuk peserta seminar, yang pertama, peserta seminar dapat memfollow akun Instagram @risbang_ui untuk mengetahui informasi mengenai kegiatan yang diselenggarakan oleh Risbang UI. Yang kedua, peserta dapat mensubscribe YouTube Direktorat Riset dan Pengembangan Universitas Indonesia untuk mendapatkan notifikasi siaran langsung kegiatan webinar atau seminar yang diselenggarakan oleh Risbang UI. Yang ketiga, rekaman kegiatan webinar yang diselenggarakan dapat disaksikan kembali pada kanal bit.ly/webinar Risbang UI dan e-sertifikat akan dikirimkan maksimal H+14 setelah kegiatan seminar. Selanjutnya, sebelum kita memulai acara pada pagi hari ini, Bapak Ibu hadirin yang kami hormati, marilah kita simak video safety induction yang akan diputarkan oleh panitia. Kepada panitia dipersilahkan.
Selamat datang. Selamat datang di Universitas Indonesia.
Welcome to Universitas Indonesia.
Sesuai dengan persyaratan K3L yang berlaku di Universitas Indonesia, kami dari UPT Keselamatan, Kesehatan Kerja dan Lingkungan akan menyampaikan induksi keselamatan.
Based on safety regulation in Universitas Indonesia, we are from Occupational Safety, Health and Environment Unit would like to deliver our safety induction.
Saat ini kita sedang berada di Auditorium ILRC Universitas Indonesia.
Now we are in Auditorium ILRC Universitas Indonesia.
Terdapat satu pintu utama di Auditorium ILRC Universitas Indonesia.
There is one main entrance in Auditorium ILRC.
Terdapat dua potensi keadaan darurat yang mungkin terjadi, yaitu kebakaran dan gempa bumi.
There are two emergency conditions which may occur, fire and earthquake.
Jika terjadi kebakaran, harap tetap tenang dan jangan panik. Jika mampu, gunakan alat pemadam api ringan yang tersedia di samping tangga darurat.
In case of fire, please be calm and do not panic, and use fire extinguisher near emergency exit.
Segera lakukan evakuasi ke titik berkumpul.
Evacuate yourself to assembly point.
Jika terjadi gempa bumi, lakukan metode drop, cover, and hold on. Jatuhkan badan Anda, lindungi kepala dengan tangan, dan berlindung di bawah kursi atau meja. Tetap bertahan hingga gempa reda. Hindari area kaca dan benda yang menggantung.
In case of earthquake, do drop, cover, and hold on method. Protect your head by your hand and cover your head below the table or chair and hold on until condition is safe. Avoid windows glass and hanging object.
Segera lakukan evakuasi ke titik berkumpul.
Evacuate yourself to assembly point.
Titik berkumpul berada di seberang gedung ILRC.
The assembly point located across ILRC building.
Selalu gunakan pegangan tangga saat menaiki dan menuruni tangga. Please always use handrails. Berdasarkan keputusan Rektor, Universitas Indonesia merupakan kawasan tanpa asap rokok.
Based on Rector Decree, Universitas Indonesia is a smoke-free area.
Jagalah kebersihan dan buanglah sampah di tempat yang telah disediakan.
Please keep the environment clean and please do not litter.
Terima kasih atas perhatian Anda dan selamat beraktivitas.
Thank you for your attention and have a good day.
Baik, terima kasih. Sekali lagi kami juga mengingatkan kepada hadirin sekalian bahwa kita masih berada dalam pandemi COVID-19, maka dari itu peserta dan seluruh hadirin yang hadir pada pagi hari ini diwajibkan tetap memakai masker selama acara ini berlangsung. Baik, Bapak Ibu hadirin yang kami hormati, selanjutnya marilah kita dengarkan opening speech yang akan disampaikan oleh Direktur Riset dan Pengembang Universitas Indonesia, Bapak Munawar Halil, melalui tautan Zoom. Kepada yang terhormat, Bapak Munawar Halil kami persilahkan.
Baik, terima kasih. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi dan salam sejahtera untuk kita semua. First of all, I'd like to express our gratitude to our colleagues from both Bruker and Dynatech. Yang saya hormati, Excellencies Mr. Kwan Chai Kwang Watanon, Sales Director Bruker Biospin, Mr. Ko Teng Aun, Business Development Manager, Dr. T. Chin Hoi, Application Scientist, Bruker Biospin, Bapak Ardiansah, GM Bruker AXS Divisions, PT Dynatech International, dan Bapak Yanwar, Sales Manager Bruker AXS Divisions, Dynatech International. Unfortunately, I am not able to meet you all today. I have to join online because of other occasions, but this is not reduce our excitement to collaborate with both Bruker and Dynatech to host this such a great event. Bapak Ibu yang kami hormati, acara ini kami lakukan secara bersama dengan Dynatech dan Bruker sebagai upaya untuk memperkenalkan basic penggunaan NMR yang kami miliki. Jadi penggunaan NMR ini ternyata sangat luas gitu ya, tidak hanya terbatas di satu bidang tertentu. Memang kalau misalnya selama ini kan penggunaan NMR untuk melakukan pengujian kan biasanya diasosiasikan dengan bidang kimia ya. Tetapi sebenarnya kalau kita lihat aplikasi dari NMR ini sangat luas. Jadi kebetulan saya juga salah satu pengguna NMR. Saya kebetulan salah satu staf pengajar di Departemen Kimia, tetapi saya well aware sekali bahwa NMR ini sangat berpotensi untuk diaplikasikan baik di bidang medis, kemudian industri, dan pharmaceutical dan lain-lain sebagainya. Jadi penggunaan NMR itu tidak hanya terbatas untuk memverifikasi dan mengelusidasi struktur dari suatu senyawa, yang mungkin lazimnya dilakukan selama ini ya gitu ya. Jadi untuk jadi sampel yang didapatkan itu harus pure, tetapi sebenarnya mixture of samples pun bisa dipakai. Nanti mungkin beberapa narasumber kita akan menyampaikan banyak sekali poin-poin yang mungkin sangat penting untuk kita bisa ikuti, sehingga kami harapkan ini bisa menjadi modal kita semua untuk lebih meningkatkan utilisasi dari NMR yang kita punya. Jadi harapan kami melalui webinar ini kita bisa melihat kembali bahwa NMR itu sangat powerful sekali ya, tidak hanya digunakan untuk verifikasi dan elusidasi struktur saja, tetapi bisa digunakan untuk macam-macam sekali penggunaan. Mungkin itu saja. Mudah-mudahan webinar ini bermanfaat untuk kita semua, dan kami sangat berterima kasih atas bantuan yang sudah diberikan dari pihak Bruker dan Dynatech atas terselenggaranya acara ini, dan kami berharap ya banyak webinar yang lain yang kita bisa kerjasamakan secara khusus gitu ya, baik NMR ataupun instrumentasi yang lain. Jadi mudah-mudahan ke depannya kita akan banyak webinar-webinar seperti ini, sehingga utilisasi dari instrumentasi yang kita miliki itu bisa kita optimalkan. Mungkin itu saja sedikit kata pembuka dari saya. Terima kasih sekali lagi atas partisipasi Bapak Ibu sekalian, para peserta, dan besar harapan kami agar acara ini bisa menjadi eye-opening untuk kita semua bahwa utilisasi NMR ini sebenarnya bisa kita manfaatkan untuk banyak sekali aplikasi. Mungkin itu saja. Terima kasih sekali lagi. Wassalamualaikum warahmatullahi wabarakatuh.
Bapak Munawar Halil. Hadirin yang kami hormati, seminar sesi pertama hari ini akan dipandu oleh seorang moderator, yakni Dr. Bayu Ardiansyah, SSI MSI, yang merupakan dosen Departemen Kimia Universitas Indonesia. Sedikit mengenai Bapak Bayu, merupakan alumni sarjana dan magister dari Universitas Indonesia. Beliau juga menempuh pendidikan doktoralnya di Nara Institute of Science and Technology, Jepang. Beliau berfokus pada penelitian mengenai heterocyclic compounds, organic acid alkaline cycloaddition. Yang terhormat Bapak Dr. Bayu Ardiansyah, SSI, kami persilahkan.
Ya, terima kasih Mbak MC untuk perkenalannya. Assalamualaikum warahmatullahi wabarakatuh. Good morning, everybody. The Honorable Director of Research and Development Universitas Indonesia, Bapak Munawar Khalil, PhD, and team, our distinguished speakers, our partner, PT Dynetic International, dan juga Brooker, ladies and gentlemen, I'm Bayu Ardiansyah. It gives me a great pleasure to be the moderator for this seminar, Basic and Advanced NMR, Nuclear Magnetic Resonance Application. NMR spectroscopy is a modern tool, modern analytical method that are extremely useful, extremely suitable for determination of unknown structure, and also qualitative and quantitative analysis, and not only for organic chemists, but also in industry, for medicinal chemists, for pharmaceutics, and so on. So in this seminar, we will study more. We will know more about several topics, like the latest NMR experiment that we have done in Universitas Indonesia by 500 megahertz NMR, sub-milligram NMR experiment, and also NMR metabolomics. Ladies and gentlemen, today's seminar will be divided into two sessions. The session 1 is about introduction of NMR, application, and sub-milligram analysis. And it will be delivered by Mr. Kwanchai Kongwatanonon. And session 2 in the afternoon about NMR metabolomic and will be given by Dr. Chin Hute. Now we are going to start our session 1. First, I'd like to read a brief curriculum vitae of our speaker, Mr. Kwanchai Kongwatananon. Could you share? Or maybe the file of the bio of Mr. Kwanchai is still in the other committee. So Mr. Kwanchai Kongwatananon is a director, the sales director of the broker for Southeast Asia, Oceania. And he is working for many years in the NMR specialist. So ladies and gentlemen, without further ado, allow me to welcome Mr. Kwanchai Kongwatananon to present his lecture about introduction to NMR experiment, the latest solution and application of NMR for this session one is divided again into two parts. This is the session one, part one, will be around 1 hour, and the time is yours, Mr. Kwanchai Kongwatanano.
Thank you very much, Dr. Bayu. So let me try to share my screen. So I hope it's shown correctly. All right. So thank you again for the introduction, and also very welcome from my side and my pleasure with the team as well from Dynatech and from Bruker Biospin. So we are like to really, help and support as many as we can. So I think today is a great opportunity that we can address in the different topics, where actually the latest NMR in terms of application as well as part of the technology actually that we have right now. So I believe that with the latest one in terms of technology, it will allow us actually, to run and using NMR in the much easier way and more automated. So let me start with my presentation. I believe I have about 40 minutes. Is that correct? 1 hour. 1 hour, right? So yeah, because in the first session, I think I will talk on this latest NMR experiment. I believe the next one will be overall by Dr. Shinho as the application overall. So let me introduce a few words about our Bruker company. So Bruker, as a NASDAQ company, we call Bruker Corporation. We have 4 groups. We have Biospin Group, Khalid Group, Nano Group, and the Best Group. So myself and the team, we are from the Bruker Biospin Group, which specialize and focus on the magnetic resonance technology. So Bruker founded in 1960 by Professor Gunther Laukin, who is a physicist, and he really done a PhD in NMR. So from the very beginning of the Bruker company, we are NMR company. So now it's this year is 63 years. So we celebrate 60 years 3 years ago. So with a lot of the milestone, actually the key milestone that Bruker offer in terms of magnetic resonance technology, feel important is that we are actually the first that we offer so-called the pulse or the Fourier NMR in the early days. And then of course, I think we continue to improve in the different component, let's say like magnet, we are actually offer more than 20 years ago, offer the first outer shield and then continue as well on that direction. And of course, some other as well. So that's today we will focus on the nuclear magnetic resonance, where on the 500, but we also offer the other, like I mentioned, Biospin, we are focused on this magnetic resonance technology. So we also have like electron paramagnetic resonance, which to me, we should call it electron magnetic resonance to align in the same way. But of course, I think we are using the paramagnetic to indicate the sample properties rather than just talking like magnetic resonance. So that's why we call the electron paramagnetic resonance. We also have the benchtop nuclear magnetic resonance. We also have a different modality on the imaging part. So basically, we also offer the MRI, but not for human, but for the so-called the preclinical, for the animal, for the material research. So for many people, let's say this is a new to you for NMR term, but you actually know this in the other form called MRI. So MRI is the same NMR, it's just that nuclear term. It's threatened people, right? So we cut this nuclear out, and then we have magnetic resonance, and then we add imaging. So basically, that's same. So we are NMR, and they are also using NMR for the human body, but so-called MRI. So we introduced this year at the ENC Q2 this year that we now can offer so-called the 1 gigahertz system at 4.2 Kelvin, which is important because in the past, this or gigahertz, we actually need so-called a compressed unit where will actually help to reduce or decrease the temperature for the normal liquid helium from 4.2 Kelvin below to about 2 Kelvin. And with that, you can actually, let's say, give more current to that superconducting, and more current means that you have more magnetic field. So now this year we introduced these gigahertz in the normal magnet. So it means that it's same like your 500. There is no different. So the maintenance, the cost of the investment and other like in operation maintenance of that will be much cheaper. So I will not just go to every details. We also actually introduced the benchtop 80 megahertz 2-3 years ago in Asia Pacific region. So of course the beauty of this benchtop is that it's maintenance free in terms of the cryogen. So many people like to invest in NMR, on the superconducting, but you know that we need the liquid nitrogen and the liquid helium to do the operational maintenance. But on this one, then it's easy because then you don't need those cryogen. And what you need is just a strong bench, strong table that you can, put this system, this bench top on. It's about 100 kilograms. So we have a different variety of the option as well, but that's will be not our focus today, but in general, what I can say is that our benchtop NMR, what we actually discussed today, most of them in terms of the NMR experiment, 1D, 2D that we're gonna jump to, we also can run on this benchtop. So it's the same. Of course, the different it's just because of 80 megahertz, the lower magnetic field compared to, like, let's say we have 500 here. So that a big difference, of course, in terms of sensitivity, dispersion, all that. But or in terms of experiment, like I said, technically, it's all the same that you can use. So let's start for our focus today, where I really focus on what we have in University of Indonesia, our Awang's NMR, Awang's NEO 500 megahertz here with the CryoPro Prodigy. So this is probably if you run NMR before, you are sending sample or you have experience directly with the system, let's say 10 years ago, or actually even 5 years ago, you probably need more times to really run all the experiment. If you, for example, the carbon NMR experiment to be run, for the very low amount of sample, you need probably overnight, 10 hours, 20 hours, 30 hours. And also, you might also facing the point where you need a lot of amount of sample to be enough to run with NMR. So in that sense, if you compare now what we have here, I'm sure that you will actually recognize that we can run much faster. So that's why I'm starting with the topic that that's a challenge, that whatever experiment time that you need in the past, one day, can it becomes like 1 hour? So I think that's just a challenge. So now just to go the individual as well as a concept, today we are not address concept, but I think with this summary slides actually give you a hint as well what it means, all this nuclear magnetic resonance. So nuclear actually is your sample. For MRI, you are, myself am the sample. So we are lying into the magnet and then we are the sample. So that means the beauty of NMR, number one, that's the most important, is that NMR or MRI is non-destructive. Meaning you enter the MRI system, you will go out the same. So I'm sure many of you using like HPLC, right? HPLC. If you were the sample, would you like to enter the HPLC? Probably not, right? Because after HPLC is no more you. Done. Bye-bye, right? Same like sample is gone. So that means that's the most important. That's why nuclear, it means sample. Magnetic means magnetic field that we're going to apply to our sample and something going to happen. And then we do so-called the resonance. So to disturb them, and then we stop that disturbing or the resonance energy, and then you actually acquire or observe the image. Just to compare to MRI, that's why you have the image, right? So NMR same, we have the image, but this image we call spectrum. So you have to understand how to read that image. Same for the doctor, physical doctor, you know, how they read the MRI image. So it's all the same, just how you actually now address it. But that's what actually we call in this slides called the acquired NMR data. And of course, you need a lot of software, you know, to process, to analyze, and all of this to the very beginning of the process, basic process, you know, is all done automatically. So that's why it's also save time. Because in the past, at the very beginning, on this nuclear magnetic, you need to do a lot of steps as well to make sure that your magnetic field is homogeneous. So with that, we call trimming. So the trimming take a lot of time, depend on your experience. And it's also different from person to person, from each of us, where we have a different experience. But now everything done by this software, well, by actually the whole system together, that do the trimming for you automatically. We call the top trim. So this is will give you all the same, regardless of your experience. So that's why it's very easy now to run NMR. And I can challenge you again, if you give me, let's say, maybe not 5, maybe 10 minutes, I can guarantee you, you can put the sample in and you get the nice data out of it, even without understanding NMR, but you know which experiment you want to get and you want to run, like proton, carbon. We will go a little bit around that in the latest one. Of course, again, the purpose today is not the whole concept and the basic, you know, so we will not probably have time. But I think tomorrow we still have another session that we have more time as well to address on those basics. So in terms of application, I think some we will address today by Dr. Shinho and myself to show some of the latest application. But in very short, it's really about our sample, right? So I will treat it always like this, very simple. It's a pure compound and mixture, that's it. So in the past, NMR is really addressed all about the pure compound, right? Using for structure elucidation, structure verification, drug discovery, but based on very much as a pure compound. If you using the NMR, well, let's say 15 years, 20 years ago, I think the professor, the top professor in your university, if you have the NMR there, will not allow you to use NMR until your sample is really pure. But now, when the latest technology software that I mentioned already as a brief one offer to the world, then it means that now we can do more in terms of QC, in terms of quantitative, because if imagine again, 20 years ago, if you want to do a QNMR, quantitative analysis, now different person who run the NMR, different operator, different experience will give for sure a different homogeneity of your magnet, and therefore also different signal in the end. So now we overcome that. That's why more and more now we address this mixture. Sometimes I call it in short as a metabolomic approach. So if you call all the name here, you can read out this, but that's just a different field that they call it foodonomic and different thing. But again, it's all pure compound and mixture. So in general, your system can run all. But now whether you can really now address on that, it depends on what is your question. So today we try to address a different question that we like to suggest, and then maybe that will fit and benefit your research. So this is some of the summary as well, what we have. You have actually at the UI 500 here. So you have the Ascent magnet. So that's the highest stability you have because it's also equipped with so-called the external disturbance suppression. So not only as an outer shield, you know, to suppress the leftover magnetic field from the magnet itself, but now another shield that's stopping any disturbance. It could be from the AC, from the alternative current, direct current, you know, from the elevator, even people are walking past by. That actually anything that is source of the electromagnetic can be a disturbance for the magnet, for the NMR system. So now we can suppress them. That's why it's the highest stability that we have right now. For the electronic, of course, the new change, you know, is around this multi-receive concept. So together with the highest dynamic range, of course, the dynamic range is not only sensitivity we address, right? Very much thinking about the mixture, thinking about your music. So your music, you have a different instrument, right? All of the instruments, some very loud, some very, you know, very glad to listen to it, like piano, you mix with the whole big drum and so on. So that the whole range of the dynamic that you can observe by your ears or by your speaker. So the bigger of the dynamic range, the better, right? So that's so-called the dynamic range that now we are at the top that we can achieve so far as the technology allow. Multi-receive is new, that's why probably today I address some of them. Maybe you're not really use all of them, but I will try to explain a little bit because that will be benefit because it's faster. Faster mean better, right? If you have to use the system, normally you have to pay per hour and so on. So if you can run it faster, why not? And you can also now speed up your research. So now you have the best system, that you have here. So why not use it at the maximum performance that allow you? And that's why I mentioned now the Crowd Pro Prodigy. So we have the specific another session just to show you what actually we run the sample here, just to demonstrate that what it means by this sub-milligram and a bit out of this sensitivity, bit out of the detection rate by this Crowd Pro Prodigy. So the NOAA experiment, I mean, if you are not using a lot of NMR, maybe you use only 1D for proton to do a verification, but 2D variety of the NMR 2D experiment, many of them available for you to use, to run in order to get the different information. For example, you want to understand the connectivity, the next neighbor from proton to carbon, right? So that one we call HSQC. And then if you want to see further, the long range coupling we call proton carbon, but not one bond, 2, 3, 4, even 5, we call HMBC. So all the name is different. COSY, maybe you know it, is a proton next to next proton. So that we call the COSY experiment. This is all 2D experiment that you have to run in the past individually, meaning you have to run each of them sequentially. So now with the introduction of our multi-receive, so more and more power sequence that introduced after that introduction. One of them so-called the NOAA. So this NOAA2 means that you can get this HSQC and COSY simultaneously in one run, single run. So that's so you will save time, a lot of time compared to each individually. So this example show you HSQC edited. Edited means you also have the information between CH, CH2, and CH3. We call the edited version. Then this one show also you have also the NOAA3. So the NOAA3 will give you three outcome. One is HSQC, COSY, and NOSY in single run. So again, in the past, you might have to run this HSQC and then finish, and then you run COSY, and then you set for NOSY. So all of this in series, but now we actually show you that it's possible now with this NOAA3 that you can run in one single run. So this is a curcumin that we run in Bangkok. So this is a real sample just to show you, we also running on the real sample, not just, I mean, the past slides is also the real sample, but this is, I run with the team. So that's just to show you that it can be done also here. So this is easily to be set up here as well. It's already there. It's just that you know the name of the experiment that we put it in, and then you can run. Like I said at the very beginning, you can run in 10 minutes. It just, that, okay, now I want in this case, HBC, HSQC, and COSY. I need this information, right? Proton, carbon, long range coupling, and then now you can select this NOAA3. Utopia is another experiment where I think if you need to run carbon, then you get, let's say, I can say that you get the 2D like TOXY or NOSY or ROSY for free. So why not you turn it on and using this Utopia, right? So then you can get one of those 2D for free. So this is a truly multi-receive because we now acquire NMR data for both nuclei, carbon and proton at the same time. So this one is not possible in the past. I mean, if you know NMR from the past, you only can run and get one nuclei at a time, proton, carbon, nitrogen, one by one. But with this multi-receive that I keep saying that we introduced with this Wong-CO where you have it, allow you actually now to do this truly multi-receive power sequence or the experiment. And this also will grow, I believe, in the future as well. People now have more tools to develop as well in terms of the physics. So we are chemists, so we use it, but I think a lot of going on as well that allow them to do more research around that. Example on this one is a TOXI. So TOXI, it's an experiment, give you the information, proton on the long length coupling, not like COSI, right? COSI is the next neighbor of the proton, but this one you follow with the chain. Sometimes we call this as the spin system. So you can like Sakurai, people using this TOXI. Then from that on the, for example, on the same row, then you can connect each proton. You see, this is all the proton, and then you can connect all this connectivity until it ends. So that we call the TOXI experiment. NOSI, of course, stereochem or how it fall, how this neighbor, not true bond. So they will give you the information proton to your neighbor, but not true bond. So you see the shape, you understand what it can be for, and so on. So this is also very important for the people who do a protein research. They're using this NOSI as a daily experiment because they want to see the shape of that protein, for example. So one of the other area where you can speed up this 2D experiment is so-called the non-uniform sampling. So the non-uniform sampling is well introduced already for protein, many years ago. But now we also enjoy it for our small molecules world. So what it means is that you now not necessarily that you need to record every single row here. Single row mean every line of that we call T1 in our parameter, but I call it rows. How many rows that you want? More rows, the better, because you have the better resolution. But then, of course, you need more time because each row, you also need to run how many number of scans in order to get the right sensitivity. So with non-uniform sampling, now we can speed up because now it will record only few up to your setup, up to your molecule as well. It's not just random. Well, it's randomly sampling for you, but we need to understand how much we set it up. At least we have some principle around it, but this is not so difficult. So we have this to speed up, and then after you record only few rows, like in this slice, and then you can so-called the reconstruct the missing row that we are not recording back. And then you can do the Fourier transform. So this show you one of the example where we use the same sample actually, just, with our software, you can shift it just to show you that what is the difference in terms of we call resolution. So this is a HSQC. It's a proton-carbon correlation. So proton is where we observe on this column we call it's a carbon carbon channel, let's say carbon channel. So you have the carbon signal on this each row, as you can see. So the blue one is run with the traditional, meaning that we record every rows. Then in this case, we set at 256 row. 256 row, it means that you have to run every row and get it 20 minutes. That's what you need. The second one, the red one, they turn on the non-uniform sampling, but the effective row jumped to 1,000. So it means we set 1,000, but we record exactly 256 row. Same for the purple one, but we set to 8,000. We turn this non-uniform sampling to 3.125%, which is exactly a cell at 256 row, but you do so-called the reconstruct afterward. So that's what you get. So which one you prefer? If you want to, because now you pay the same money, right? Let's say now you submit the sample, you still have to pay it for 20 minutes run. Which one you prefer? I hope all of you would agree with me that the purple one is the best because that's the best resolution. But it's not necessarily even to get the purple one. The red one also very good already. So why not just, trying to speed up rather than get the resolution? So the next slide show you exactly now. Between 20 minutes and 2 minutes, you get exactly the same quality. So now you can choose. You want to run 20 minutes or 2 minutes to get the same. Of course, everyone with the Facebook generation, we all need to speed up, right? No patience. So we need 2 minutes. That's what we want. So yes, that's correct. But also showing in these slides, that if you run 20 minutes with the NUS on, in this case, we said that 2048 with sometimes we call 2K rows. And then you have about 10% of the NUS, and that's what you get. So again, in this, just to show you different setup, don't need to read all of that, but some is a different setup. But which one if I'm not telling you to read through it, all the same, right? There is no benefit in any of each of them. It's all the same. So you pick 27 minutes or 2.5 minutes to run. Of course, 2.5 minutes, right? So for us, for the small molecules world, NUS really benefit you to speed up all the 2D experiment, all this information that I already mentioned. So we also have this, with the courtesy from Burapha University, Dr. Surayut actually run this on the real sample. So we, this is already quite big with the molecular weight more than 1,000 Dalton. So if you compare this, the traditional one, the whole total acquisition, I cannot really, let me hide this. So it's a 4 hour, 19 minutes, but if you turn on 25%, then you can shorten the acquisition time to 1 hour and 20 minutes. Also for this one, further run as well on the NOAA 3, meaning HMBC, HSQC, and COSY, and then even turn on the non-uniform sampling. Very nice spectrum, right? So, I mean, that's all what you need. So, I mean, it speed up the time, from 3 hours. Now you can run this. If you combine everything, on this NOAA at only 23 minutes. So you get all of the information same. Even this one a little bit better in terms of resolution. So that's what actually the NUS should be your so-called the new normal. You run 2D, you should think that, yes, I can apply this on uniform sampling to speed up my research or to use the time to gain more sensitivity, not to get on these normal, traditional recorded rows. So that's what it means. And I you that we are not talking a lot, but maybe later we will address over the next session, but the sensitivity is increased as a power of 2. Meaning, if you want to get double sensitivity, in this case, I show as a HSQC, see? If I need to run 1 hour, it means that you need 4 hours in order to double your sensitivity. But if you turn on this one, you need only 6 minutes because you turn on 10% NUS. Then if you want to double your sensitivity, you need only 24 minutes. So 4 hours and 24 minutes, it's a big difference, right? I changed the unit. Now, if you have 4 years compared to 24 hours, well, no, 24 days, have to be days, right? Yeah, that would be something that critical is not exactly math, but just to give you the impression that is a big difference. So that's, well, I mean, that should be your common to consider to use it. On this slides, actually, this is data that probably I mentioned again in the next, but I think at this point in time, what I like to address is that your carbon experiment, you have more variety, meaning you can use a different, we call the pulse sequence on the right side. It's all give you the carbon spectrum, maybe a little bit different in details, but that's all carbon that you can actually try to run. So you have all these experiments on your system. So you might interested to maybe run on so-called this R-ring because from the sensitivity point of view, this R-ring 90, in this case of quinine, that's the best. And also for vanillin, as well as for the beta-carotene. I will probably address this a little bit later in the next session. So the cryoprobe as well, that what we, we'll focus on this prodigy. So this one, we also have the other cryoprobe, which really can go maybe sub-microgram. For us, 500 prodigy, in the simple sentence summary, it means that you now have better than 800 mega system in terms of sensitivity with the normal probe. So that's what you have. So you should enjoy and benefit it as much as you can. So how it works, we cool the detection coil, we call the probe. Actually, it's a resonant coil as well. You can call many different names, but it means that this one, I'm calling it as a detection coil because that's the most important when you receive or detect the signal there where you have the less noise. So we cool it down to 85 Kelvin using the liquid nitrogen. And that's where you gain your or enhance your sensitivity. Enhance your sensitivity in this case mean you suppress your noise. How you can increase your sensitivity? There are only two ways, signal part or the noise part, right? Signal part, what you can do? I mean, this is not just for NMR, for anything in life. Signal, of course, you increase your amount of sample. Of course, you can go with the higher magnetic field, but probably that's it. Noise, we can do a lot. You suppress the noise, right? You listen to the music, you listen to somebody talking, it's how you filter it out. So we can suppress the noise because sometimes you cannot control the signal, right? The signal is there, but you can control the noise. So exactly now, where we invest this technology, where we can suppress the noise, and that's a big difference, and it's cheaper compared to invest to gain the signal through the bigger magnetic field. Like you go exactly to buy the 800 megahertz system, that's going to be a big investment compared to this cryoprobe Prodigy. So we call the name this one as a Prodigy. So we're using the liquid nitrogen to cool it down, so that way we can suppress the noise 2 to 3 times. 2 to 3 times, it means that it's huge actually in terms of the sensitivity. So jump to that, just to speed up a little bit. I think the time is also limited. So the driver or the challenge for NMR, of course, sensitivity, as we know, that we already addressed, but we also have the other thing, especially on the application side of things, apply application core in these slides. So metabolomic, QNMR, mixture analysis, targeted, non-targeted, all that, that's our challenge. That's why we develop all this like stability, why it have to be highest, because you want to run today, you want to run tomorrow, you want to run next month, next year. If it's the same sample, it should give you the same, right? Anything, it should be different from your sample, not from your system. So we call this highest stability that you have. So that's also, actually, this is also the second point where NMR have delivered the better compared to other techniques. We call this reproducibility. So if you thinking about this reproducibility compared to the other techniques, I think Dr. Shinho will probably explain a little bit more, but just to give you a hint first that you can probably thinking ahead. So in terms of sensitivity, we come quite far actually from the very beginning. We compare in these slides, this chart, in 1965, we have the sensitivity 5 to 1. In 2009, we have the first 1 gigahertz system that I mentioned earlier slide today, but that time it's still a very big magnet, 15,000 kilograms just for the magnet, 15 tons. So compared to the gigahertz now we have is only 2.3 tons or 2,300 kilograms. So it's a big difference. But anyway, just to compare the sensitivity on that using the cryoprobe, this one is helium cryoprobe. The sensitivity achieved is about 12,000 to 1. So if you compare this between these two, the timing is what? About, let's say, about 50 years apart, 50 years. But if you look at the outcome, it's more than that. Meaning that if you want to run, mathematically, you can calculate that. If you want to run the 60 megahertz system in 1965 to get the same sensitivity, it's need a lot of years. It's not a little year because that's the power of 2. So that's a big jump actually that we have in terms of the productivities. So together between this Prodigy and non-uniform sampling, this is your new normal, and that's you have as your system here. So you should actually now always using this Prodigy probe and with the non-uniform sampling whenever you run on the 2D NMR. Of course, 1D, we don't have that. But 2D, 1D, we address some of the techniques later on to show you what actually you can get as well. Proton, carbon of that. No? So same here. Now I go with the 9 hours, you see, carbon, because it's carbon. So carbon, if you need 9 hours, you want to double sensitivity, then you need 36 hours. You have to time 4 because it's power of 2. But if you really use the Prodigy probe, normally to get the same sensitivity, you need only about 1 hour. 1 hour. depend on your complex, your molecules, but let's say 1 hour compared to our standard sample. Then it means that you need 4 hours to get the double sensitivity. So now 36 hours compared to 4 hours is a big, right? If I change now, both of them 2 years, now I can do both 36 years and 4 years. That's where you can get your million. Which one you want? Well, you get the research, I can compare to number, million, right? US dollar. So, I mean, that's our new normal. So now we have it. This is not about that you don't have it, you have it. So now this is what you have. So you should enjoy it. So this showing, this is running here. This is running in Thailand, but just I think afternoon, not the next, the third session, I will talk about what we achieve and run here as a demonstration that what you also can run here at the 500. So this 110 milligram, 8 minutes, in the past, you won't be able to run this 8 minutes on carbon, this is no chance. Depth Q 4 minutes, I jump quickly now with the 64 scan, and just to compare, even with this number, you won't be able to run and to get the same nice spectrum on this carbon, with this compared to this cryoprobe. So HSQC 3 minutes, so this is of course with the NUS you see here, so-called non-uniform sampling turn on. So that's why for me, I only encourage everyone run 2D with the non-uniform sampling because it's quick. Now it's 3 minutes, COSI 4 minutes, HMBC 7 minutes. Now why I want to run this carbon 1 scan, because now we want to run inadequate. So we are running now with the quite higher amount of sample. Now you see we are running on 60 milligram quinine, just to check on the sensitivity, whether we have the chance, to observe inadequate experiment. Inadequate, then I explain some, right? Inadequate is like COSI for proton. You have the direct information connection, next carbon to next carbon and so on. So this is a shortcut for many people who doing structural elucidation would love this inadequate. But this experiment, normally, if you are teaching NMR in your bachelor degree or NMR course, this is only in textbooks. You never can be performed this in your real sample. Now, with this prodigy, just to demonstrate that, that's really nice. Now you can also run, I think we run some as well on your system. So this one run less than 12 hours. I believe that we can shorten even, but well, I don't have a lot of time, to play with the instrument. That's why I only can encourage you here that you can run many, just to test as well. Then you get more information and then you can share as well for any other user who want to run NMR. So I think that's also a benefit to utilize the best on your system. So that's the Zoom version, but we also have the adequate. You see, it's 3 hours. Now we observe, you get the similar information a little bit. You have to think twice, of course, because now we observe on proton, which connect to that carbon, but that you have also this connectivity directly in the end between carbon and the next carbon through bond. Psyche, another experiment. I think some experiment some application like mixture analysis. I think the Psyche or the pure chip may be very useful. This is a broadband homodecoupling on proton. In the past, if you do proton, you can only, not only, but difficult to achieve this in the past, but normally you only do homodecoupling. So you decoupling on this peak and then see what changed on the other. But you see this one is a broadband decoupling. So that means it's simple, more simple form on proton. That's what you want. Sometimes you want to gain the better resolution, separation, dispersion. So this is an experiment that probably can benefit you. So this is a new thing. So this is running again on this one of the tablet. We call Fatalight Joan. This is a herbs that in Thailand, people know this, or Thai people aware of this, because you take this tablet when you have the first symptom of COVID-19. You take it right away. That's well known in Thai. In general, this one, they have this endocalcin compound that actually help in terms of sore throat, but also to resist or to get better. So that's what we run and showing you all the different experiment that only name the new things. I'm not really going through all the basic 1D, 2D of them, but I hope that you see also what actually the advanced experiment that you can now consider and that you probably might need in the future in some of those, and then you should actually consider all those NUS or those new things, and then it shorten your time. So another quick one, I think Shinho will probably go very details around this. This is a ginseng run mixture, using all this metabolomic approach. In this example, I mean, you can tell with the Simca chemometric statistic tools, which one is not belong to the group because the outliner. In this case, I want to study or classify a different ginseng, whether it's from North America, or with the Asia Pacific or Asian one. So this is run with, I think, quite a few years back, thanks to this University of Ottawa, together with Brooker colleagues in US, so we are demonstrate using these techniques and this software. So the software now allow you, the point for me to showing all this software, it means that the latest as a solution, now NMR can develop that. So it can go just to be like this. You don't see the spectrum, but we'll just to verify that, yes, this is my raw material. This is the right thing. So if you are doing or some collaboration, or you just want to check your deuterated solvent. Let's say you buy the deuterated solvent, right? They claim that this is a 0.1. Well, let's talk the different 99.9 purities on this, let's say chloroform, you buy it deuterated solvent, then you can actually now using NMR to check the leftover of this proton, right? So that can be done. And then you can see also using this NMR as a raw material screening. So that can be done as well. So you can use this as to check the quality control. Another example, no time for details, but this also can be part of the adulterants, unknown compound, all that, you can set it up, and then whether this is really, yes, what you want in your, in this case, herbs, one of the herbs. So it's a hidden ingredient. So this one is reported, 10 years back already, but I think it's still a very good example that they add this sibutramine in their herbs, so it's not really natural herbs anymore, right? So they add this up. So NMR can obviously observe this peak, very easy. You see, this is a run, the real herb sample, just extract. Then you see this right away. So many times when we're talking about this, we call as a fingerprint. So this is your fingerprint. I drink water, you drink coffee, you buy from different places, you have Rua coffee, it should give you, hopefully, that the different fingerprint. Otherwise, it's no benefit, right? Hope that there is some different marker there, not just a taste. One of the last, we run also this cannabis oil. I'm based in Bangkok. I'm from Thailand. I'm Thai, so cannabis now, well, legally, but of course, we still have a lot of other laws that have to be implemented. But in general, now it's open more in Thailand with this cannabis. So I, collects just to check whether, let's say you buy the cannabis oil, is real or fake, because it's not cheap, right? Many people still want to buy this because of health benefit. We are talking now, maybe the cancer type of people, a group of patients, where they have no, from the Western world, Western medicine, let's say, or the modern medicine, not just Western, right? We have our own as well, but try something else. So cannabis oil is probably one of the recipe that you think of, So to me, it's just, you buy this, whether it's a real one or not, you can recognize already, some of the marker is different. So, the component in cannabis oil or the cannabis is always have the CBD and THC. So that's our marker there. So following on this paper from the group of Robert Robute, then you can see they really go in detail. You can search a little bit more on that. But just for me, it's just, looking as a reference where we can have this CBD, THC as a marker. Then, actually Dr. Shinho done this using our Azure software just to see and as it's a lot of step, of course, but I just jump now, but just to really give you as a report like this, yes or no, based on the CBD, or could be also based on the THC. So this is now on the THC, that's on the CBD, same step, but now looking at different regions. So then you can also using this as a marker as well to prove that this oil is really a fake or the real cannabis oil. So that's hopefully you get a little bit more into NMR, not just doing structure elucidation, verification, but this is also verifying, right? Whether this is a cannabis oil is a real one or not. So with that, I hope I'm on time. So thank you very much for your attention.
Well, very interesting and comprehensive talks given by Mr. Kwanchai Pongwatananon. And yeah, I think NMR spectroscopy not only useful to elucidate the structure as we have done in our laboratory, for example, in organic chemistry, but also as Mr. Kwanchai said that the NMR can be used to identify the hidden ingredient, for example, in the drugs. So we can conclude that maybe the drugs is dangerous for us or safe for us. And from the talk, there are many experiments can be done with our NMR, especially Bruker Advanced Neo in Universitas Indonesia. We can run NOAH and also Utopia, and the time for running the NMR experiment is very important. For example, for carbon NMR, maybe very, very long. And also for two-dimensional NMR, also long. And with NUS, non-uniform sampling, we can speed up the acquisition time. So, for example, 36 hours become 4 hours. And the 2D experiment can be done within 1 minute here. Yeah, I think the first part of the session went very nice talks. And before continuing this session, from PT Dinatek International, probably Bu Fatimah will tell us about the top spin installation. Probably. Yeah. So this time will be the direction from Bapak Fatimah on how to install. Yes, because this is 2 days seminar, so tomorrow we will conduct the experiment directly, not only for proton and carbon 1D, but also 2D. Before that, you will maybe will be given some theoretical, and after that we can study and analysis together with the in this time. So we will study how to install the Bruker top spin application to process your data tomorrow. So please, Bu Fatimah.
Bapak Ibu, sebelumnya mohon maaf ya karena memotong waktu coffee break Bapak Ibu, tapi ini insya Allah tidak akan lama. Jadi besok kita akan juga berlatih menggunakan software NMR yang dimiliki Bruker, yaitu software top spin. Nah, untuk itu supaya besok bisa kita mulai, kita lancar untuk mencoba softwarenya, maka saya mengencourage Bapak Ibu untuk bisa mendownload software itu di hari ini ya Bu ya. Bentar saya share dulu screen-nya. Oke. Oke, nah jadi Bapak Ibu, besok kan kita akan juga belajar bagaimana cara memproses data baik itu data satu dimensi, menggunakan raw data langsung dari yang kita sudah lakukan analisis menggunakan NMR broker yang ada di UI. Jadi bagi Bapak Ibu yang mau langsung mencoba bagaimana cara data processing menggunakan software Topspin yang ada di yang dimiliki broker, silakan Bapak Ibu bisa mulai mendownload hari ini, saat ini juga, atau mungkin nanti setelah seminar juga boleh, atau mungkin malam, karena memang proses downloadnya agak lama Bapak Ibu, tergantung dari ini komputer masing-masing gitu, ada yang cepat, ada yang lama, tapi saya menyarankan baiknya untuk di-download hari ini juga. Nah, pada dasarnya ada 4 step ya Bapak Ibu. Pertama Bapak Ibu harus registrasi akun dulu di broker. Jadi Bapak Ibu nanti saya arahkan langsung saja ke web broker ya. Bapak Ibu bisa akses software Topspin di web broker. Nah, nanti Bapak Ibu silakan tinggal buka browser, kemudian ketik broker.com. Nah, akan muncul tampilan seperti ini. Nanti Bapak Ibu bisa menuju ke service support, kemudian software support and upgrades. Kemudian Bapak Ibu pilih di nuclear magnetic resonance dan belum ada. Oke, jadi intinya nanti Bapak Ibu silahkan download. Prosedurnya sudah saya rangkum secara lengkap. Semua stepnya sudah saya rangkum secara lengkap dalam bentuk PDF. Saya share linknya melalui chatroom mungkin ya, chatroom dan juga grup WhatsApp. Bapak Ibu yang sudah bergabung di grup WhatsApp silahkan nanti bisa diakses linknya di sana. Dan bagi yang belum juga dipersilahkan untuk join. Jadi nanti ketika Bapak Ibu ada kendala dalam proses download atau dalam proses instalasi, silahkan bisa ditanyakan, kita sharing bareng. Ada kendala kita coba selesaikan bareng-bareng gitu. Jadi insya Allah besok kita akan coba langsung dengan menggunakan raw data, baik 1 dimensi maupun 2 dimensi. Pemrosesan data processing sampai dengan penyajian data. Sudah begitu. Silahkan nanti diakses Bapak Ibu, linknya bisa di-share ya Mas ya. Saya kirim via WhatsApp tadi. Oke. Sudah itu aja Bapak. Supaya besok kita tidak ada kendala untuk mencoba memproses data. Semoga kita semua bisa mencoba. Jadi sebaiknya memang di-download hari ini. Terima kasih waktunya Bapak.
Ya, terima kasih Ibu. Ya, actually, we still have time for question and answer. Yeah, actually, the discussion session today is after session 2. However, if you have any questions, so maybe you can raise your hand, or maybe from chat in Zoom. Is there any question? Not yet. If so, we will have a 15-minute break. So please use this time for refreshment time. And we meet again in this room at 11:15. Yeah. Thank you. Ya, terima kasih. Nanti 11:15.
Baik, hadirin yang terhormat, kita akan break sejenak. Silahkan hadirin sekalian untuk menikmati hidangan coffee break yang telah disediakan di luar auditorium ini. Bagi hadirin yang ingin menikmati hidangan coffee break, dipersilahkan untuk di luar auditorium telah kami sediakan. Sekali lagi kepada hadirin yang silahkan keluar auditorium. Telah kembali ke auditorium. Materi kita yang pertama, saya ingin mengumumkan terlebih dari pendaftar paling tercepat. Ya, saudara Restu sudah ada di sini. Dapatkan hadiah sebesar 100. Oke, dan hari ini untuk tetap memperhatikan jalannya sesi seminar pada sesi pertama hari ini dan juga sesi kedua. Dikarenakan nanti akan banyak sekali hadiah yang bisa jadi menjadi rezeki hadirin sekalian. Oke, langsung saja. Saya serahkan sesi pertama ini kepada Bapak Bayu, kami persilahkan.
Ya, terima kasih, Mbak. Welcome back to the ELNC auditorium. Without disturbing your refreshment time, so we are going to continue the session 1, part 2. We still have our prominent speaker, Mr. Kwanchai Pongwatananon, and this part will be deliver of the presentation material, and after that we will have a question and answer or discussion session. So I think
the sensitivity gain by 2 to 3 as a factor between normal probe and the prodigy probe, it would be equal as a power of 2 to 4 and 9 up to 9, 4 up to 9, right? 2 to 3. It changed to 4 to 9 in terms of the productivity. So I can say as well, let I take the maximum number on the third line. They're saying 9 system of the normal 500 still cannot run the sub-milligram. So it means that your one system, the 500 with the prodigy, is better than even the 9 system, right? In this sense. So I think why not? I think, understand this, and now you can enjoy more and not afraid of this low amount of sample at the 1 milligram level. So the productivity is the second term. I mean, it goes hands in hand, actually. So we already mentioned a few times that the productivity is power of 2. To 1 that our running on the standard sample, but convert again because it's threefold. You see, the sensitivity is threefold, right? But if you convert this again by power of 2, it means that I would need 9 hours on the normal probe compared to just 1 hour on the cryo probe. It should show 800, not 1000. A comparison. So that equivalent to your 800 mega system. So I can say, like in the morning, change the unit, not hours, to years. So for carbon, if you let the system just run on carbon all the time, it would be 9 years compared to 1 year. 1 year by the prodigy probe. Hope you get the message. At least, you have the impression what you actually have at this 500 at your here that you can actually now achieve. So we run, with the team, Fatima here as well, and together with my team, Dr. Mongkon, trying to run a few series of experiments just to, with the limited time that many thanks as well to you, University of Indonesia here, that allow us to try and demonstrate this. So then we picked 2 samples here, vanillin and the beta-carotene. So this is how it looks on the proton experiment on the vanillin. So it's a 10 milligram. Here on the blue, I have the overlay with exactly the noise level. It means that I treat it with the reference on the blue one and the same noise level. So this is what you can see. So 10 milligram, yes, you can see some peak, right? I'm sorry, so see some peaks there. I just checked that you also see the same like mine. So the red, yeah, you still can see a little, right? You can recognize something there. But with the same noise level on the 0.1 milligram, hardly you see anything. What you see is DMSO and the water in the DMSO. That's what I label there. Okay, so that's not what we want, right? We want to see our vanillin signal, not our solvent. So we are using the DMSO as a solvent in this case. This just to give you now the picture on this different amount of sample. Well, 10-fold each, right? 10 milligram and then 1 milligram and 0.1 milligram. So that's what we achieve. Now, if you zoom in, before the zoom in, I just show you the property. You can search as well in Google. Or if you install the top spin, I think Fatima mentioned how to install, I think, the top spin, because for academic, it's free. You will also have the NMR guide. I'm not sure the others still can see. Yes, the NMR guide will also have some property, the table of the NMR. So one of them is this the solvent properties. So that's why you can see what is left over in terms of the residual signal from this DMSO, just as a reference. So I zoom it up now. Same, you see the same noise. It means that all the same, you know, blue, red, and green, they have exactly the same noise level, right? Exactly the same. But you see, the signal is look also different now, huh? You might ask, oh, why is all different? You see? So many points. One is this, I hope you see also the cursor. Let me, I think green is okay, huh? So in this area, of course, I can recognize right away there is some also other impurities because 0.1 milligram is really, really low amount of samples, of course. Then you can see others, you know, that not belong to this vanillin. The other area that I can see right away as well, oh, more peaks here, right? Yeah, some here, same, some a little bit here, but more peaks here. You see? So all of this we call the carbon satellite because it's so sensitive that now we can observe proton that attach to the carbon-13. The normal proton here, what I'm go back to this slides again. Let's see the blue one because, oh, I have to wait a little bit. It's okay. So that's the blue one, huh? So it means that what I'm trying to say is, I can see that is a little bit delay. So the blue one, you can see that it's very simple proton. Without zoom it up, it's only, well, like, you know, like that, right? Not so many peaks because this peak is a proton that attached to carbon-12. Proton attached to carbon-12. And you know, carbon-12 is not active in NMR. So this one, there is no information in terms of which proton connect to which carbon. There is none. Correct? Now you zoom up or zoom in. You will see this satellite here. So it will be exactly the same. If it's doublet, it's going to show doublet. If it's singlet, it's going to show singlet. But it's a proton now that see the carbon-13. And of course, with one carbon-13, then it becomes doublet, right? Because it's influenced by next spin system. So that's why you have this so-called the carbon satellite. What I'm trying to also say here, in the very low amount at 0.1 milligram, you don't see it. Okay, so this is most of the case now where you have in your, without the prodigy, I would say, because the prodigy is more sensitive. So it would be give you more information. And we love to see this, of course, but there is more as well in terms of mixture analysis and so on, because you have to, it's more complex, but we also have the way to treat it. I think Dr. Shinho will probably mention few, but in the end, we want to see more, right? Because that's showing the dynamic range as well on one hand, right? So if you can see on this carbon, in this case, it's really sensitivity point here, because then you can see all these carbon satellite, which is representing proton and carbon-13. Okay, so that's why you have this. So next time when you have you run and proton, you have this one sharp line, and then you have besides them exactly the same distance. You know, it's the carbon satellite, and the J coupling on that CH is exactly from this small to the other one, from the satellite to the satellite. So that the JCH. So just a few words around this, then you not really surprised when you see and blow it up, you know, and then you see on your proton like this. That's another view. Now is better, right? It's the same, huh? I just now make it, I shift it a little bit so you can see this is all the satellite. Left, right, you know, the green one, you don't see it anymore because it's too low, cannot detect. Yeah, it's still the same sample, right? But different amount of sample you see also differently. Yeah, but you have to think of it and then try to explain. But that's how we have to understand some of the, well, the concept as well. Huh? Hopefully that demonstrate a little bit as well in terms of the sensitivity we have, you know, with the Prodigy probe. So then we perform the carbon, you know, on this 10 milligram as well, you know, using ZGPG. So the ZGPG is just one simple observe carbon and decoupling proton. The observed peak is 30 degrees. I might not jump to detail because I don't think it's good to go in the deep level yet, because we not really cover on the basic. But if we jump right there, it may confuse more. But the message is that this is one pulse sequence, one experiment that you can run. You can pick, okay, I want to run ZGPG30. Please run for me. So it gives you one carbon. Okay, like this. So I check on the sensitivity. This is 272 to 1. Now we run now another experiment, ZGPG. Same to get the carbon. But now at the same time, same, right? Exactly 256 scan, about 14 minutes. Same here. This one, oh, you nearly have the double sensitivity. So to explain this, it's because of the pulse sequence itself, but also related to the relaxation. Well, we don't have time to cover that, but just to mention again here, to show you that the different carbon available can give you a different sensitivity. So this one, same, another carbon, now we call the depth Q. So the depth Q, why it look like this? Because the positive signal, it represents CH and CH3. The negative one represents CH2 and quaternary carbon. That's why you see, I can tell you all of this is quaternary carbon because we run the other experiment. So I know that there is no CH2 in this. I hope I'm correct. I'm not chemist, by the way. Shinho, ask Shinho again in the afternoon whether this is my summary, well, based on my experience. So the other signature on this depth Q is that you always have the solvent as a quaternary, so you can face it negatively and correctly, yeah, because it's always quaternary, right? Because it's deuterium, right? It's deuterated solvent. So the majority is deuterated solvent. So the C, there is no connectivity to proton. It means it's quaternary carbon in this case. So if you not understand what I'm talking, then you really need another training course, the concept first. That I also happy to help next time. So now this is what in the morning I show you this, but not really jump to a lot of the explanation. So all of this, each of them is a different pulse sequence. Give you the same carbon experiment. We call carbon experiment. You can pick one. So the message here, what I'm trying to show, actually also in the other meeting, is that there is no one pulse sequence that superior for all sample. So that's why we have a different version of the carbon experiment. So you can choose a UDEF, DEPQ, ZGPG30, ZGPG, a ring, and a ring 30. So this one on the vanillin. I think in the morning we also run on the quinine. I show you on the quinine as well that also the sensitivity, the best sensitivity is on the R ring, 90 degree, which this one, no? This one. Yeah. It's some delay on the mouse. Sorry for that. Let me try. Maybe pointer, maybe better. So on this one. So the R ring, it's delay. Yeah, I check on the screen there. Okay. So this one, it's somehow on the quinine, on the vanillin, and also the beta carotene give you the best sensitivity. Coincidentally, but still, I have to say it's not conclusion. Any remark on this? We can discuss a bit later if you like to ask. So we jump then to the 1 milligram as the demonstration. So wow, we run still 14 minutes. Wow. But somehow Fatima and Dr. Mongkon pick 30 because they have no information on this one first. Because if they know, they should run a ring. Because if you look at the number there, it's about 2-4 compared to the ZGPG30, 664 compared to the 347. So it means that if you pick the right one, even with this scan, you will have a higher sensitivity. intensity. But it's also good, no problem. But it doesn't mean that we know from the beginning which one we have to choose. This one you need more experience. Well, not experience, but experiment data that we can really make a conclusion. We need more than this. Huh? But this one, I just want to make the statement that we have many pulse program, many experiment for carbon as well that you can choose. And no one is the clear answer. But in this slide, somehow the R-ring is like a conclusion, but just only from 3 compounds. We have quinine, we have beta-carotene, and then we have vanillin. So we need more time if you like to do. You don't need 1 milligram to check on that. You can run on 10 milligram. Yeah. Depth Q, yeah. So that's also same 14 minutes. So this is all the quaternary same, you know. Well, now it's become noisy, right? With the same 256 scan, but still you get all. 1 milligram, you know, 14 minutes. I think this is wow. But okay, I mean this one. We have to say that I think the preparation is also very clean, I believe, because they go with the big amount and when they do the dilution steps. So I think with that preparation, I think we can say more or less confident that this is about 1 milligram that they prepare. Then the HSQC, 2 minutes, huh? So they run even one scan, you know, 1 milligram, you know, you turn on the non-uniform sampling. So you see, wow, very nice. So that's why I said, I know this tree is quaternary carbon because it's not pop up in the HSQC because HSQC is only proton and carbon connectivity. So that's why my conclusion, yes, this tree is quaternary carbon. And now you see, this is a moisture. This is a DMSO. This is a DMSO peaks. This is moisture. So some artifact, you see, some artifact. So yeah, also here, because it's huge. So it means that this is only two minutes, right? So you probably need more time if you want to have the cleaner spectrum. So this is what it is for 2 minutes. But if you run longer, of course, these all the real peaks, you know, will overcome or higher all those so-called this from this moisture peak as a T1 noise here. 0.15 now, so we go a bit another dilution. So of course run more now, nearly 1 hour. So now you see the artifact is also gone. That's what we are seeing on the previous slides. So now it's no more. Now it's better, but still 1 hour for 0.5 milligram. You know, this is huge achievement in my opinion, because if you run before with a normal probe, this is hardly you're going to see anything, you know, on 1 hour, not possible. 0.1 milligram, you know, so I have this projection proton on 10 milligram in case you ask, you know, why it's so huge in terms of the peaks, you know, if you remember from the first slide. So I picked that one. This one runs 7 hours now, 7 hours. We have no time actually from Fatima run, you know, we have no time to try 1 hour, 3 hours. I think we like to try, but probably it's your job there later on to try different things, because now I said we have one shot. Let's do, you know, the whole night. So they pick a 7 hour just to be sure that we get a nice spectrum, you know, on this 0.1 milligram. This is 100 microgram. This is very challenging. Tell you, this is not normal with the normal probe that can measure. So if now we run carbon, you see, now also run 30,000, well, 30K we call in short, you know, 30,000 scan, but 1K is equal 1,024. So you have to times that. So it's a 30K, 27 hours now, 27 hours. But if you compare this one, or if you remember all the peak is there. Of course, you also see now the impurity, and the phase is a little bit tricky. It's too low. So that I didn't have time to play more. I think I have to maybe send to Dr. Gino to phase a little bit more. But this one is a very low amount, you know, 0.1 on carbon. This is very challenging. Yeah. So now I compare everything now in one a shot, you know, from 10, 1 now on carbon. We already have proton, but now I add also the 0.5 milligram there. Different, of course, have to be a different number scan. Now you cannot compare the same. Otherwise, on the 0.1, you run even 1,000, you see nothing, I believe, really, maybe the Sowen peak, but now you see it's all, that's what I'm trying to say. You see, a little bit here, right? You see as well, but it's there, but 30K now. So we are about at the limit. I keep saying, I mean, if you need more, then you need another cryoprobe version. But this is already very, very good, in my opinion. Hardly you're going to run a 0.1 milligram. Normally 1 milligram, maybe 0.5, and you have to wait and prepare precisely. So in the other term, I think weight of your sample also help to collect later on. So I'm not sure it's a rule here, but I would suggest, but I know for the structure elucidation, maybe normally people don't do it. Weight exactly, I mean, you need a super balance, to weight on this. And at 0.1 is very difficult to really check on this level, right? A little impurity is done. So you see as well some other impurity that you're not observing from the other one, see? So that's for sure, that's normal, it's not that clean, let's say. So then, well, I mean, it's lead to other implication that, well, this is a detection limit as well, that we see such a impurity, right? So hopefully that you have some idea, what I try to give as a message here. Another zoom up, so now you see a bit better on this peak, but still very low. But remember, all of this, they run only ZGPG 30. They should run with R-ring. Yeah. And this one, actually, Fatima, we run this already, actually. We should, well, you probably have no time to digest that, but I learned later that the sensitivity is nearly double. So I would suggest, if I know before, that we have to run with the R-ring. So all this is very difficult because it's also the quaternary carbon, right? So now we are aware of that. So yeah, so I think that's a lot of the understanding if we really look close, on this carbon as well. Then we run, as I said, in the morning, I show that I run in the system in Thailand, but now we also run here in Nadiquet. But they run without non-uniform sampling. But it's also good to show, even without non-uniform sampling, you have this 14 hours like this. So if you turn non-uniform sampling 50%, you need only 7 hours. Yeah. So it's a good implication, but we have to probably experiment it, cannot calculate it in the way that because it's all power of 2 and other subject as well add in, all this power sequence is complex. It's not that linear. So we cannot calculate. I mean, the one with the standard sample where we know we can, but on the unknown, and this one is on unknown, but still difficult to really calculate back, how long it's gonna take. Let's say I put different setup, for example, like the NUS, you can calculate for sure. But in terms of sensitivity, what I mean is that if I run now NUS 50%, it means that it's going to be 7 hours, about 20 minutes, right? Or 16 minutes. But I'm not sure. I am not sure that the sensitivity will be the same. That's what my message. Principle, it should be. But that's why we have to try and run more, you see. But still, it saves time, isn't it? Because if you turn on, you still can have a double in terms of using on that time to gain on number of scan. So this one we have to try. Yeah. So the Zoom version of now the beta carotene. So I will not show proton because repeating now, I don't want to bore now on those, but just to show you, because this is about 500 Dalton. I mean, the vanillin is about 100 something Dalton. So this is bigger. So you see more carbon, right? So run exactly the 1000 scan. So for sure, 1 milligram is better. And mind you again, we run with ZGPG 30. We should have nearly double sensitivity if we use R-ring 90, because that also I run it as well with the setup. I think I show in the next slides, no? But this one just to zoom as well. Now we run the depth Q. You see as well. But now if you ask me which one is CH2 and quaternary, I cannot tell except this one. Of course, this one I believe this is all CH2, right? Hardly you have quaternary on this region, and this one is a chloroform. Why is a quaternary? If you cannot answer right now, you have to take more course in NMR. Why is I call it quaternary? So hopefully you see something as well that I'm trying to put on the message here. So we run COSI as well, 12 minutes, I cannot guarantee that this is all. I need a professor who know this and should be, but at least when I blow it up, zoom it up in this region, I can see, yes, it's all. At least correlation. HSQC is easier. So with this HSQC, I can say now on this spot 1, 2, 3, 4 is a quaternary. Well, I need Chinho to confirm on that. But from the HSQC, because I don't see the CH2, I don't see the peaks there. So it must be quaternary carbon. That's why you need HSQC. So if you hear a lot, I show a lot of HSQC rather than experiment. Dr. Shinho would agree with me, and actually his word, the HSQC is the heart of experiment, because very simple, you have full information. You have full information from proton, carbon, and correlation between proton and carbon in single experiment. So this is the important experiment, even for the mixture where you want to gain more, let's say, to understand, to identify, or to even to get a better resolution. I think you still need to go with the HSQC. So this is what I also calculated later on after we run all this experiment. It's running here, all of this running here on this system with this beta carotene now. So now the ring also, is not far from, let's say, the UDEP or the ZGPG. The point is that for you, for here, from my feeling now, for the natural product type of, 100 to 500, maybe you should consider not using 30 degree. The 30 degree, we suggested because it's not believe, it's correct that we'll gain a little bit better enhanced, not enhanced, the better sensitivity on the quaternary carbon, because it's allow you the relaxation shorter. But on this, you have to probably have to do more works, calculate all that. But from what I, as overall, I checked already this region, so it confirmed that somehow this ring and ZGPG, is a better choice compared to the 30 degree, even the quaternary one. The quaternary one, I think we have to check again, using on the depth, now we know that some of them is for sure the quaternary. Then we should do more works to calculate the sensitivity. But this is only 3 compound that I had now. The screening run all this series. This is all just pop up, that I think it would be good to show. We run and show you that is not only one fit all on carbon. So with that, I hope that you see that this is quite impressive on the system that you have in terms of carbon, especially. I think now we have more carbon as an example, because carbon is always the most challenging when you have the low amount of sample. So with that, thank you very much for your attention.
Okay, thank you so much, Mr. Kwanchai, for informative and detailed presentation about the sub-milligram NMR experiments. So before break time, we still have a discussion for this session. So I'd like to read the question from Zoom. Yes, there is one question from Mr. Andi from ITS Surabaya. He asks, if I have 2 to 3 milligram amount of sample using 5 millimeter of NMR tube, could I get good peak in carbon-13 experiment?
I think it's, you see here, right? I mean, again, this beta carotene, I'm not sure what is your size of the molecules on your compound, but this one 0.5, run only 1,000 scan is about 54 minutes in this setup and 27 minutes in this setup. So yes, you will get it. And I remind you, if I were you, I would suggest let run 90 degree or the R-ring, right? First, I mean, you pay the same money. You don't have 2 shots, right? You don't have 3. You cannot have the comparison only if here allow it, right? So, I mean, yeah. So I would suggest that I would go with the 90. But it's not guarantee. It's not guarantee. It's I have a different experience on that. Yeah, that's not 30 is better than 90 as well. But not these 3 compound. I hope that answer with also this slides.
Yeah, thank you so much. So it is clear that 2 until 3 milligram of sample, it's very enough to
Yes.
measure the carbon NMR.
Right,
and,
right.
and get the good pick for you. So next, I'd like to invite a question from the audience in this room. If you have question, yes, okay.
Over, bring the mic there. 2 to 3 milligram. The question you ask, you have to be sure that you weighed it correctly. You cannot just, okay, you know, this is about 2 and 3, and then submit here, and then you expect the same. And it turned out that you only have 1 milligram. Many cases, because I want to save my money, right? But if you won't save your money, because if you're telling them 3 milligram, they will say, 1 hour would be good because this 0.5. And it turned out really bad because you're not really weighed it, then it's your fault. And then you have to pay again, double. So mind you, be careful. If you're not really weighed it and it's not pure, you know what it means. So always talking the truth. That's important in my opinion. And then we can get the right experience as well. Yes.
Hey, my name is Deki. I'm from University of Indonesia. I want to ask, how come the development of NMR is happening very rapidly, and from the various NMR aspects that are already very good now, is there any possibilities of future improvement? Thank you.
For proton, you mean?
Yes.
In terms of improve in terms of what? In terms of the pulse program, the experiment to improve the quality, right? That's what your question.
I mean, actually, it's Noah, Kosi, and
The 2D.
yeah.
Yeah, the 2D detected. Yeah.
Yeah.
And the question again, the improve means?
Now it's very. Is there any possibilities of future improvement?
Of course, yes. I mean, now you see, I show the NOAA 2 and 3, right? You know, you guess what is the latest now? Is NOAA 10. So now you can get 10 experiment, 10 spectrum in single run. We call NOAA 10. So there is also NOAA 10 available now. So it will be ongoing. That means whatever it comes, probably you don't have the pulse program now, but you can always ask for support, our support to implementing it. Or if you're really familiar now with the top spin, you also can add on your own. Because some of them is not Bruker, right? This is all the research group of people, you know, doing this NMR on physics side of things, like I said. So in the future, I believe there is more to come. Yeah, because of this multi-receive, like I said in the morning. So yes, but now we already have NOAA 10. Yeah. Maybe you don't need it, but just to let you know, because then it's always something new pop up. Yeah. So like we also talking about the Psyche. I don't think Shino will also talk, but the Psyche that is a broadband. We also have many versions, especially from Manchester, University of Manchester, I believe, that they have this a lot of 2D toxic Psyche or this, meaning you're doing the toxic, but you're also doing broadband decoupling, which is important because it could be very complex, right? Now you make it simple, then you can correlate better. So it's a lot of new things coming up for sure. Yes, if you're interested, then would be nice you jump in that field as well. I think that would be very nice. Yeah. I hope that answer now. Yeah.
Okay, thank you.
Yeah, thank you. I think it's still enough for one more question. So if you have any question about NMR experiments, so do not hesitate to discuss in this session. From Zoom, maybe?
Chat?
No? Okay, maybe from my side, you just explained about the proton and carbon. How about the development of probably fluorine NMR,
Mm.
is it possible to run the fluorine NMR with Bruker Avance 500 in University of Indonesia? So-
I think you have the system. I mean, the Prodigy itself, you can run fluorine. Yes, you can. So this is also detected one of the nuclei, and of course, this become very popular. The point is that the Prodigy, the design of the coil, the fluorine will be on the proton. So it means that you cannot run fluorine with proton decouple on this probe. But if you have a different probe, they have other probes, many probes. They can. I'm not sure here you have only Prodigy, I believe, right? Or you have other probe as well? You have room temperature probe or? No, right? Yeah. So then, well, the probe is, again, it's a detection coil where if you're really interested, like, it's a must that you have to run a fluorine and decoupling proton or vice versa. Then you need to, buy more probes. You can then just change the probe. So there is many other places, if the budget enough, they also need to invest a little bit more because each probe is also addressed differently. Yeah.
Yeah, thank you. Because the fluorinated compound is very commonly found in commercial available drugs. So I
Correct.
think the determination of fluorine spectrum in NMR is very important. Yeah.
Right,
So-
right. And you are right. I mean, drug discovery
Yes,
is more and
yes,
more.
Yes. Is there any question from Zoom? Could you show us the question?
Should maybe I stop sharing my screen?
Okay. Yeah. Is it possible to perform NMR experiment for inorganic compound?
Which nuclei? Yeah, I mean, you see, I mean, this is a broadband probe that you have. So actually you can run many nuclei. So it's depend on, yes, I mean, people also doing that. I mean, again, now we are talking because the system here is a solution form, right? So it have to be diluted somehow in the organic solvent or as a solution form. And yes, people also, running on this, it could be, I don't know, silica, I'm not sure, silica, aluminum, sodium, I mentioned boron. I mean, all those I mentioned, I have experience, helping customer as well to observe and run. So for your Prodigy, you can run all those actually. And to explain a little bit more, what is a broadband means, if you still have time, I could, let me share my screen again. Just to show you which nuclei, right? I said it's a broadband, right? But which nuclei you can run with the Prodigy, right? So I can quickly show you the NMR table. So let me share my full screen. I think I have it open here. So this is when you install the top spin, you can open this one. We call the NMR guide. It's a web format, a web browser, where you can go to NMR table like this one. So I can go now to the frequency. So this is a 500, but let's a common broadband. Normally it means that you can run any nuclei from 15N, 15 nitrogen, up to 31P for us. So this is not the isotope we're talking NMR frequency. So it means that now you're talking 500 equivalent to this one, see, 11.7, 500 here on this one. So it means that you can run anything from this frequency, 50.6 megahertz, 50.6 megahertz up to 202.456 megahertz. Anything in this range you can, like I just mentioned, like boron, whether it's 10 or 11 isotope, you see it's fit in between 50 and 202, right? Can run. This one can, of course, carbon. This one cannot, below now. Yeah, this one, yes, our minimum. And so on and so on. So this one can, and so that's how you read or what it means by the broadband that you can run. I hope that clear a little bit or explain a little bit and you understand more now.
Yeah, thanks so much. I think there is more question from online platform. Is it okay to one more question?
Sure. I can answer, even skip lunch if you want. Oh, from the chat, right? Oh, sorry. I should be able to see too, right? So here and chat, how to open, here, right?
Yeah, this question. In your screen, position of the solvent in the red spectrum is upward, while the blue one is downward. Could you explain that?
Okay, but I think it's probably mean carbon or what? I think solvent red. Oh, you mean this one, I believe, huh? Because it's on this one. Well, the red one is a carbon experiment. Carbon experiment, everything is positive. When we face correctly, it have to be all positive. So this is all carbon. And then the blue one we call depth Q. So the depth Q is give you we call the edited, NMR world we call edited information. So the positive, it will be CH and CH2, sorry, CH3. So it means that this carbon position, it can be CH or CH3. So I'm the carbon, right? So I have 1 proton or 3 carbon attached to me on this position, each of them. Here, let me change again to this pointer. So all of this upward on the blue one, yeah? All of this. Yes, so this can be CH or CH3. On the negative part, it will be 2 possibilities. It's a quaternary carbon or CH2, meaning carbon without proton attached or carbon with 2 proton attached. So that's the depth experiment. So that's why sometimes I always, encourage people run on the depth Q rather than the others. But of course, we have to experience a little bit, on the different things. I think this one already showing, I don't know, it could be quaternary, I don't know, because it's quite low on this peak. So because the quaternary is a little bit tricky, we also have a different parameter that we have to make sure it's the same and so on. But hope that answers your question. So basically, the depth experiment is a carbon, give you the information how many proton attached to that carbon. And that's why there is a negative and the positive. And in this case, you ask the one that, many of them, right? I mean, this one is up, but this one is down. That means this one, it can be CH2. CH2, I know this can be only one is a quaternary carbon on the solvent peak. Yep.
Yeah. Okay, thanks so much for the answer. I believe you still have many questions or interest about the NMR experiments, but because the limitation time, so I encourage you to ask or save the question and please ask the question at the end of the session too. So
Yes.
Mr. Kwancha is still available.
And Ochinho, yes, of course. But
yes.
put it in. If we cannot answer in these 2 days, we will continue to answer all those questions. Just put in the chat. I think it's we collect it, right? Yeah. So please just dump the question about NMR, of course. Thank you.
Yeah, thank you. So finally, we come to the end of the session 1. So I'd like to say thanks again to Mr. Kwanchai Kongwatananon for the interesting and informative lecture this morning. And also for the audience for the participation. So don't forget, we still have session 2 after break, start from 1:30. So from my side, it's enough now, and the time I will give back to MC. Terima kasih.
Once again, dan terima kasih banyak Bapak Bayu Andriansyah telah membersamai kami di sesi pertama hari ini. Dan Bapak Ibu hadirin yang kami hormati, materi sesi pertama telah kita ikuti bersama. Selanjutnya adalah break makan siang dan juga Bapak Ibu yang beragama Muslim dipersilahkan untuk menunaikan ibadah sholat terlebih dahulu. Kita akan kembali pada pukul 13.30 waktu Indonesia Barat. Diharapkan Bapak Ibu sudah kembali ke dalam room Zoom maupun auditorium ILRC Universitas Indonesia. Baik, dipersilahkan kepada Bapak Ibu yang ingin menunaikan ibadah sholat atau makan siang, dipersilahkan waktunya 1,5 jam. Terima kasih.